Good morning, my dear students. Today I'm going to explain about the force analysis of a Hartnell governor. Okay. So in the last class we studied about the force analysis of a Porter governor. So in this class I'm going to derive an equation of force analysis of a Hartnell governor. Okay. So in examination, either maybe Port governor and this Hartnell governor they can ask you. Okay. So derive an expression for a Hartnell governor in terms of spring stiffness by using a force analysis method. Okay. So now I'm going to derive this equation with the help of force analysis method. So before going to derive this equation, let me understand what you mean by a Hartnell governor. Okay, so in the last class, that is the introduction class, it is a classification of governor class. I am going to told about the what you mean by Porter governor, what you mean by Hartnell governor, and what is the difference between them. Okay, so now I'm just going to tell you about the what is the definition of the Hartnell governor. Okay, so in the Hartnell governor, here we are going to add a spring force at the middle of, that is the axis of the shaft of the governor, to control the force. Okay, so in here the controlling force can be done by spring forces. Okay, that is called as a Hartnell governor. Okay, so here just to understand that spring Hartnell governor is the thing, but we are going to add some force that in terms of spring at the middle axis of the Porter governor, that may be a helical spring, whatever may be that. Okay, so that is called as a Hartnell governor. So here the two ball in this two mass of the ball connected within a bell crank revolve, whereas in a Porter governor it is not like that. Okay, so this is the main difference between the Porter governor and the Hartnell governor. Okay, so let me derive this the equation for this Hartnell governor by using force analysis method. Okay, so the initial side is the Porter governor, and normally we taken as two mass ball, that is a fly ball, so that can be connected within a bell crank lever. Okay, so based on that diagram I am going to draw here the two free body diagram. That is first one is the minimum position, that is the minimum rotation of the speed, and the second one is the maximum position, that is the maximum speed of the rotation. Okay, so these are the two different block diagram which can be occur from the Hartnell governor when the speed is maximum, when the speed is minimum. Okay, so when the speed is decreases, the arm, that is the arm of the shaft of the Hartnell governor should be goes decreases, that is come down to the near to the axis of the shaft, and this the top one sleeve can be moved downward direction. Okay, so hence I am going to draw here this O to A is a right hand direction. Okay, for in the minimum position condition, whereas here the maximum position condition we drawn O to A right of the axis. Okay, so because here the if the speed of a shaft increases, the rotation of the ball going to be rotated very high speed, and that will be outward direction, and the top of the bottom, that is sleeve movement, that can be lifted some distance, so that is OC. Okay, so OA, that is the main difference between the minimum position, the maximum position. Okay, so I am going to repeat again. For the minimum position, OA can become down near to the axis of the shaft. At the maximum position, that OA can be goes pull outward direction, that is with the help of that what there will be a centrifugal force will be generated okay, at the point A. Okay, so this is about the block diagram, and remaining all are distance only. Okay, so 0 to A is called as in A, let us assume as A1. Okay, so while rotation of the shaft, that when if you switch on the shaft, that while rotation of the shaft, a centrifugal force will be generated at mass of the ball, center mass of the ball, that is at A1, that force is called as a centrifugal force 1. Okay, that is controlling force. Okay, at the same time there will be a gravitational force will be there, that is W is equal to mg. Okay, that is about mg shown here. So the bell crank lever mounted on point O to the exit of the shaft is called taken as a radius distance. Okay, radius distance, that is R. Okay, so now come to down the sleeve movement. Okay, when it comes down, that is 0 to C, that distance is called as a total lift, that is called as a height. Okay, so and the axis right hand side I shown here, that is called as a governor axis. Okay, so at the middle this block diagram I have taken only half of the bell crank lever, that is a Porter Hartnell governor. Okay, so hence we are going to consider here mg plus s1 is divided by 2. Okay, why how if you consider full means we are going to take only the mg plus s1, but we are going to take the half of the diagram, so hence I am going to take an as mg divided by 2 plus we are going to add some spring forces at the middle of this middle of the axis of the shaft, hence we are going to consider as S1. Okay, so this is a brief introduction, that is brief terms we are going to use in a Hartnell governor. Okay, and these are the forces will be generated at maximum position and minimum position. Okay, so similarly just to observe at the maximum speed we are going to take these are the forces which will develop in the at maximum position. Okay, so this is about the block diagram of Hartnell governor with the help of force governor, with the help of a force analysis method. Okay, now let me understand what are the quantities we are going to use in this. Okay, let m1 is the mass of the each ball. So here there are two m will be there, one small m and one capital M. Okay, small m is a mass of the each ball, capital M is a mass of the sleeve in kg, r1 is a minimum radius of the rotation and r2 is a maximum radius of rotation, n1 is equal to minimum speed of governor at minimum radius, n2 is equal to maximum speed of the governor at maximum radius, fc1 that is fs1 is called as a spring force at minimum radius at n1, that is speed minimum speed, fs2 that is spring force at maximum radius at n2. Okay, so these are the terms we are going to use. Also along with that, so fc1 that is centrifugal force, it is a controlling force with the fly masses corresponding to the minimum speed, that is n1, and which is formula is given by m r1 omega square. Okay, so omega is equal to 2 pi n 60. We know that in previous semester we studied this, so earlier semester we studied this. So just to substitute, these are the two formulas we generated of centrifugal force at mass ball a1. Okay, similarly fc2, here also same, wherever f1 is there you just to put it 2. Okay, centrifugal force due to the fly masses corresponding to the n2, that is the maximum speed, same formula, that is fc2 is equal to m r2 omega square, and which is equal to m r2 2 pi n2 by 60 whole square. Okay, ks is equal to what? Stiffness of the spring or the force which is required to compress the spring by unit length. Okay, in a Hartnell governor normally we are going to use a spring that can be compressed within small unit length, so that assume as a ks. Okay, and a is nothing but length of the ball arm of the bell crank lever. I shown in the diagram also, just to observe here, length a1 here, so see the right hand side, left hand side, a is equal to nothing but length of the ball arm of the bell crank lever, and b is the length of the sleeve arm of the bell crank lever. Okay, so don't make confuse, a is nothing but ball arm, b is equal to sleeve arm. Okay, and h is equal to compression of a spring when radius of the rotation changes from r1 to r2. This is depend upon the number speed of an engine speed. Okay, so when the minimum speed is very low and maximum speed is very high. Okay, so that distance, that is the sleeve lifting sleeve is taken, a formula is called as total lift, and which is given by h is equal to b by a r2 minus r1. Okay, so now these are the formulas, that is these are the terms we are going to describe the Hartnell governor. Okay, so now let me derive the equations, that is at taking the moment about o, that's for minimum position. Look at the only the block diagram one, taking the moment about o is equal to fc1 into distance. Okay, height of the distance a1. Similarly here, that is you make a horizontal forces and vertical forces equal. Okay, so this is about fc1 is a centrifugal force into distance is an horizontal forces, and mg plus s1 divided by 2 into distance b1 is a vertical distance. Again, that the gravitational force weight is equal to mg into distance is nothing but total distance minus r1. So that formula we are going to take. Once you solve this, once you generated this formula, then just you rearrange the following equation. Okay, so mg plus s1 divided by 2 b1 is equal to fc1 a1, you go you send it in the right hand side, so that is fc1 into a1 minus mg r minus r1. Okay, again we are going to rearrange this, mg plus s1 is equal to this, go this b and 2 send it to right hand side, you are going to get 2 by b1 centrifugal force fc1 into a minus mg r minus r1, give equation number 1. So this is about the minimum position. Similarly, you find the maximum position and take the moment about the o. Moment about nothing but force into distance, that is called as a moment. Okay, take the moment about o, then we are going to get this equation. So now you calculate here mg plus s1. For the figure b, you are going to take the mg plus s2 formula. Okay, so again mg plus s2 divided by 2, force into distance is nothing but b2 plus mg r2 minus r1, that is a distance, is equal to centrifugal force, that is fc2 into a2. Again we rearrange this, mg plus s2 divided by 2 b2. Okay, fc2 you are going to send that side, so fc2 into a2 minus mg r2 minus r1. Again you re-simplify this, mg plus s2 is equal to what, you b2 by 2 you are going to send this side, so 2 by b2 fc2 into a2 minus mg r2 minus r1. Okay, so give equation number 2. So subtract the equation number 2 and equation number 1. So you are calculated what, mg plus s1 equation, mg plus s2 equation. Okay, subtract the equation 2 minus 1, you are going to get this what, mg plus s2 mg plus s1. Okay, 2b by 2 fc2 into a2 minus mg r2 minus r1, and minus of 2b1 fc1 into a1 minus mg into r minus r1. Okay, so now after this, that mg plus minus that is mg get cancelled because opposite sign. Okay, so from this again we are going to re-simplify this, s2 minus s1, and remaining term all you are going to send the right hand side. Okay, so we get from this equation, s2 minus s1 is equal to 2 b by b2 fc2 into a2 minus mg r2 minus r1. Okay, so minus 2b1 fc1 into a1 minus mg r minus r1, give equation number 3. Okay, so far you calculated what, mg plus s1, mg plus s2, s2 minus s1. Okay, but for this we know that spring stiffness of an Hartnell governor is equal to what, ks is equal to s2 minus s1 divided by height. That's height is called as a total lift, what that going to lift from axis of the shaft to the top. Okay, so here again s2 minus s1 is equal to ks into h. Ks is equal to what, s2 minus s1, but we know that h is equal to what, b by a r2 minus r1. Okay, so here therefore the ks is equal to what, a by b s2 minus s1 divided by r2 minus r1, give equation number 4. So but for the Hartnell governor we have in some assumptions, that is the distance may can come what original position. So hence we are going to assume as a1 and a2 is equal to a, b1 b2 is equal to b, and also neglect the moment due to weight of the fly masses. Okay, where the moment of the fly masses that going to be neglected. So substitute these values in the above equation, that is from equation number 1. We are going to get what, mg plus s1 is equal to 2 by b1 means b f centrifugal force into a into moment you consider as 0. Okay, so you get mg plus s1, that is 2 fc1 a by b. So similarly from equation number 2, mg plus s2 is equal to 2 by b fc2 into a moment assume as 0. Okay, so minus 0. So again mg plus s2 is equal to 2 into fc2 a by b. So give equation number 6. So again we are going to subtract the equation number 6 minus 6, that is 5. Okay, so mg plus mg we are going to get cancelled, so remaining is s2 plus s1 2 fc2 a divided by b minus 2 fc1 a by b you are going to get. So again we got s2 minus s1 is equal to 2 a by b fc2 minus fc1. So this is the equation for this simplified equation of what that total lift, equation number 7. Okay, now so put equation number 7 in equation number 4. So from the equation number 4 you got what, ks is equal to a by b 1 minus r2 minus r1 2 into 2ab by fc2 minus fc1. Okay, so just you going to substitute this s2 minus s1 value in equation number 4. So we get 2a by b whole square fc2 minus fc1 divided by r2 minus r1. Okay, therefore the spring stiffness ks is equal to 2a by b whole square fc2 minus fc1 divided by r2 minus r1. So this is equation is called as the spring stiffness of a Hartnell governor. Okay, this equation you have to remember while solving the problems of Hartnell governor. Okay, equation number 7 also you remember, equation 8 is also you have to remember, 5 6 also you have to remember. Okay, based on the given data we are going to use the formulas and solving the answer of the particular Hartnell governor problem. Okay, so this is about the derivation of Hartnell governor, and this is also very important for the point of examination. Sometimes they may ask you to derive an expression for a Hartnell governor in terms of spring stiffness by using a force analysis method. Okay, or that Porter governor what we studied in the last class. Okay, so these are the very important derivations today we solve. So just to analyze this, you have to able to draw this free body diagram of force, yeah, at minimum position and maximum position. Okay, so I hope you understand this derivation. Okay, I just 2-3 pages are there, we have to practice 2 more. Okay, thank you very much.